Episode 8.
Exploration Strategies. Every algorithm we've built so far has a dirty secret. SASA, Q-learning, even Monte Carlo, they all use Epsilon-greedy exploration. Pick a random action 10% of the time, pick the best action 90%. It works. But it's crude. Think about it. When Epsilon-greedy explores, it treats every unknown action as equally worth trying. The action you've tested 1,000 times and the action you've never tried once, same random chance. That's like a restaurant critic who occasionally picks a restaurant by throwing a dart at the phone book. There are smarter ways. Strategies that explore where uncertainty is highest. Strategies that scale exploration with confidence. Strategies that are actually curious. This episode is about all of them. In the last episode, we built SASA and Q-learning. Both algorithms learn Q values, action values, by interacting with the environment step by step, and both use Epsilon-greedy to decide when to explore. Here's how Epsilon-greedy works. With probability 1 minus epsilon, pick the action with the highest Q value. With probability epsilon, pick a random action uniformly. Simple, but limited. It doesn't consider how uncertain we are about each action. It doesn't explore more where we know less. The Exploration-Exploitation Dilemma is fundamental. Exploit too much, and you miss better options. Explore too much, and you waste time on bad choices. Epsilon-greedy draws a hard line between the two. What if we could blend them more intelligently? Let's start with what we know. Epsilon-greedy is the baseline for exploration. Set epsilon to 0.1, and 10% of the time you take a random action. The problem is obvious when you think about it. Imagine a 10-armed bandit. You've pulled arm 3 100 times, and you're pretty sure it pays about 1.2. You've pulled arm 7 exactly once and got a reward of 0.8. Epsilon-greedy is equally likely to explore either one. But arm 7 is the one you should explore. You know almost nothing about it. This leads to the concept of optimistic initialization. If you start all Q values at a high number, say +5, then every action looks promising until proven otherwise. The agent naturally tries everything at least a few times because the untested actions have inflated values. It's a simple trick, but surprisingly effective. Decaying epsilon is another common fix. Start with epsilon equals 1, pure exploration, and gradually reduce it towards 0. The idea is to explore a lot early when you know nothing, then exploit more as your estimates improve. But the decay schedule is a hyperparameter, and getting it wrong can hurt badly. Upper confidence bound takes a fundamentally different approach. Instead of exploring randomly, UCB explores systematically. It adds a bonus to each action's estimated value based on how uncertain we are about it. The UCB1 formula is elegant. Select the action that maximizes Q of A plus C times the square root of the natural log of T divided by N of A. The first term, Q of A, is the estimated value, what we think this action is worth. The second term is the exploration bonus. It grows when an action hasn't been tried much, because N of A is small, and it shrinks as the action gets tested more. The parameter C controls the exploration-exploitation balance. Higher C means more exploration. Lower C means more exploitation. When C equals 0, UCB becomes pure greedy. Here's the beautiful intuition. UCB constructs a confidence interval around each action's value. The bonus term is like the upper end of that interval. When you're uncertain, the interval is wide and the upper end is high, so you explore. When you're confident, the interval is narrow and the true value dominates. This is called optimism in the face of uncertainty. UCB has a theoretical guarantee. It's regret, the difference between what you earned and what you could have earned with perfect knowledge, grows only logarithmically with time. For bandits, that's essentially optimal. Boltzmann exploration, also called softmax exploration, takes yet another approach. Instead of a hard threshold between greedy and random, it assigns a probability to each action proportional to its estimated value. The probability of choosing action A in state S is e to the power of q of S, A divided by tau, all divided by the sum over all actions A prime of e to the power of q of S, A prime divided by tau. The parameter tau is the temperature. When tau is very high, all actions get nearly equal probability. It's like a very hot gas, where molecules move randomly in every direction. When tau is very low, the distribution becomes sharply peaked around the best action. It's like a cold crystal, where everything locks into place. Boltzmann has an elegant property. It naturally differentiates between actions. An action with Q value 5 gets more probability than one with Q value 3, which gets more than Q value 1. Epsilon-greedy treats all non-greedy. Let's put them head-to-head on a 10-armed bandit. Each arm has a true value drawn from a standard normal distribution. Rewards are the true value plus noise. Epsilon-greedy, with epsilon equals 0.1, starts badly. It picks random arms and accumulates regret fast. Around step 200, it finds a good arm and starts exploiting. But that 10% random exploration keeps pulling bad arms, even after thousands of steps. The regret line keeps climbing, just more slowly. UCB with C equals 2 starts differently. It tries every arm once, then focuses on arms with high uncertainty. By step 100, it's already narrowing in on the best arms, while still occasionally checking less tested options. Its regret curve flattens faster than epsilon-greedy. By step 1000, the gap is significant. Boltzmann, with a decaying temperature, starts similarly to UCB. High temperature means broad exploration early. As temperature drops, it concentrates on the best arm. Its regret curve sits between epsilon-greedy and UCB for most of the run. The cumulative regret chart tells the whole story. Epsilon-greedy, linear regret, the line never truly flattens. UCB, logarithmic regret, it flattens beautifully. Boltzmann, somewhere in between. UCB wins this benchmark, and it has the math to prove it. Thompson sampling is the dark horse of exploration strategies, and arguably the most elegant. Instead of computing a bonus or a probability, Thompson sampling maintains a belief distribution for each action's true value. Here's how it works. For each arm, maintain a beta distribution with parameters alpha and beta. Alpha counts the successes, beta counts the failures. To choose an action, sample one value from each arm's distribution. Pick the arm with the highest sample. This is beautiful because exploration happens automatically. When you're uncertain about an arm, its distribution is wide. Sometimes you'll sample a high value, which triggers exploration. When you're confident, the distribution is narrow, and you'll consistently sample near the true value. Thompson sampling matches UCB's logarithmic regret bound and often outperforms it in practice. It's been widely adopted in industry. Every time you see an A/B test at a tech company adapting in real time, there's a good chance Thompson sampling is running underneath. Now let's go beyond bandits. Curiosity-driven exploration attacks a different problem entirely. In complex environments with sparse rewards, even UCB and Thompson sampling struggle because they depend on getting some reward signal to learn from. The intrinsic curiosity module gives the agent its own reward. The prediction error of a learned forward model becomes an intrinsic reward. If the agent can't predict what happens next, that state is novel, and novelty is rewarding. The intrinsic reward is the squared error between the predicted next state and the actual next state. This is how agents learn to explore Montezuma's Revenge, a notoriously hard Atari game where external rewards are incredibly sparse. The agent learns to seek out rooms it hasn't visited because they're unpredictable and therefore interesting. These strategies scale into deep RL in fascinating ways. Noisy networks, introduced by Fortunato in 2018, replace Epsilon-greedy by adding learnable noise to the neural network weights. The network itself decides when to explore. The noise parameters are trained alongside the Q values, so the agent learns to be noisy where uncertainty matters, and deterministic where it doesn't. Random network distillation, or RND, extends curiosity to scale. A randomly initialized network defines what familiar looks like. A predictor network tries to match its outputs. States where prediction error is high are novel. RND drove breakthroughs in Montezuma's Revenge, reaching scores previously thought impossible without human demonstrations. Go Explore took a different approach entirely. Instead of intrinsic rewards, it maintains an archive of interesting states and periodically teleports back to them to explore further. Combined with imitation learning, Go Explore solved Montezuma's Revenge and Pitfall with superhuman scores. The exploration problem isn't solved. In fact, as environments get more complex, exploration becomes harder. But every strategy we've covered today, from simple Epsilon-greedy to curiosity modules, gives us another tool for the problem. And that's what Module 2 has been building toward. A complete toolkit for learning from experience. Next up is Module 3, where we face the curse of dimensionality. Our Q-tables worked for small grids, but what happens when the state space has millions of dimensions? The answer is function approximation, and it changes everything. See you in Episode 9.